Used by Girish Kulkarni, 121 centimeter. Observables, right? And then what we want to do is we want to typically identify some physics parameters. And then what we want to do is develop a mapping between the physics parameters and the observables, the values that the observables is. And this is what we mean by modeling. There is a sort of opposite arrow as well in this diagram, where we have an observable and we try to find out the values of the physics parameters that correspond to that observable. Okay? And this is known as inference, right? So this diagram essentially is what I guess science is about. We do experiments, we measure quantities, and we find the values of various physics parameters. I think one could say that it's a dream of physics to arrive at a theory where there are no parameters, where everything is understood fundamentally. But until then, we have a variety of physics parameters, some of which we postulate just to develop, construct a theory, and then we measure the values using these observables. So this mapping is what I'm going to do today, and what I hope to convince you is that the choice of these physics parameters is non-unique, that because the cosmological 21 centimeter problem is so complex, there is a variety of ways one can parameterize the problem. Okay? I think we will have an inference exercise in the tutorial as well, where you would be using some sort of Monte Carlo method to take a mock measurement of the 21 centimeter signal and try to measure the values of the physics parameters. Okay? So to set up the basics, the physics parameters that we have in 21 centimeter cosmology is parameters related to the sources of the radiation that affects the 21 centimeter line. Then we have the parameters of the cosmology, the background cosmology, and then finally we have the parameters of reionization, the things that affect the abundance of neutral hydrogen itself. So what I'm going to do in today's lecture, hopefully, is to talk about the galaxy formation parameters here. Okay, and we will see how of 21 centimeters. So this part follows the galaxy formation parameters. We will assume that all other parameters in the problem we understand 100%. Now, if I want to do this, if I want to study the galaxy formation parameters, the best redshift is cosmic dawn, because there we don't have any complications due to reionization, etc. So I will mostly focus on these high redshift values today. Okay, so that's roughly how we will go. So just to set up some of the things, we have the INI is the specific intensity of radiation. Then we have, for the 21 centimeter case, the radiative transfer, the basic radiative transfer equation, right? So we have some terms which relate to the cross section, which denotes the probability with which the atoms of hydrogen will interact with the radiation. And then we will have terms like what Prasoon described very nicely in the previous lecture, right? We will have these Einstein coefficients. So the quantities inside these big square brackets are deciding are using the number statistics of the occupation of the two hyperfine levels, and then quantifying the probability with which the hydrogen atom will move between the two energy levels. Okay. So the A10 is the Einstein coefficient, which I think Kanan wrote in the morning, which for 21 centimeter has a very small value. The other extreme in astrophysics is the Lyman alpha, which is, I think, 11, 12 orders of magnitude bigger value than this. So this is very weak, which is good, because this is the reason we can hope to see the whole universe in 21 centimeter. And as once we have A10, we can write B10 and B01 as well. Right, and G0 and G1, we just learned what their values are. It's 3 and 1 respectively, and we use the same notation to define our occupation statistics using statistical mechanics, which allows us to introduce the quantity of spin temperature. Right? So the idea is that the value of the spin temperature will decide how the two energy states are occupied. That will decide the probability with which the hydrogen atoms will interact with the radiation. Okay? And of course, we have seen this as well multiple times, but the convention is to do all of this in units of temperature, in which case we can write using the Rayleigh-Jeans formula. All the intensities, the specific intensities INUs, can be written in terms of the brightness temperatures TVs by doing INU times C squared divided by 2 TV squared. Okay. Okay. So the fundamental equation that determines how I nu evolves. So I nu, of course, is going to be contributed by the CMB in the case of given cosmological experiment. And the fundamental equation that determines how that I nu will evolve by the time it arrives at the observer is the radiative transfer equation. This radiative transfer equation can be written now in terms of the brightness temperature. And when that is done, it takes the following form. Okay. So this is the brightness temperature that emerges at the end of a ray of light connecting us to the CMB. This is the amount that is attenuated while it arrives at us, and this is the amount that is refracted. Okay, because of the transitions between the two hyperfine lines. Okay, and here a new quantity has now emerged, namely the tau nu, which is the opacity. H.T. Lightman is a really good book if people want to understand radiative transfer equation really well. Okay. So here tau nu is an integral along the side line. So ds is the length element, and it's an integral of the absorption coefficient, okay, which is related to these cross sections. Okay, so this is the or opacity is also called. Okay, and this discussion came up in I think Kannan's lecture, but if the hydrogen atom in its comoving frame has emits the intensity Tb prime at frequency nu naught, then the observed intensity, just because of the equation of state of the photons, will be Tb at nu, which would be related to this brightness by a factor of 1 plus z. We will have a similar relationship between nu naught and nu. Of course, I have written here the optical depth tau in terms of this alpha, and I just waved my hand and said that this alpha is related to the cross sections. But that's actually true, and I can explicitly write that down here as alpha nu equals h nu by 2 pi. Okay. So the point is that the net absorption depends on your occupation statistics N0 and N1, which means it depends on the spin temperature. So the absorption depends on the spin temperature. We have heard this before in Prasum stuff. I'm just making it explicit. Here, I have not yet specified the line profile phi nu. People probably know that this line profile has the functional form of the void function, but we can approximate it often as a simple square wave absorption with a bit delta nu, where delta nu is related simply to the velocity, peculiar velocity of the atom. And if we do that, then we can now do this integral tau nu, and we can write 1 0 now denotes that this opacity is about the photons that connect the two energy levels as this. Write it down in simpler font here. Yeah. And then it's super in my notes. It, one would have to check. You think it should be 4.5? Okay, so could be 4.5. Could be 4.5. Yeah, yeah, could be. I would rather trust your notes. Could be 4.5. Yeah. 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 4.5 would make. Okay, so this tau 10, if you add values to some of the numbers that go into the expression there, comes out to be very small. The dimensionless number. And here we start seeing these parameters emerge. Yeah. How would be calculated? Yeah, that's a good question. I think we will discuss that. Believe that it can be calculated. We will come to that. Okay. So we will have 1 plus delta, and we haven't calculated anything. That's the same question for other terms as well. 1 plus z to the we have h1 is 10 times this peculiar velocity. So there are a couple of points to be noted here. One is this number is very small. As you know, absorption becomes exponentially strong as you increase tau. Where tau occurs in the radiative transfer equation is e to the minus tau. And so because this number is quite small, it is very difficult to saturate 21 centimeters. That is one of the great attractions of the 21. All other lines in astrophysics, they saturate pretty easily, but this line doesn't. The other point to be noted here is the emergence of the parameters. So we are now, if we go and remember the diagram that I drew at the start of the observables and the physics parameters, here we have something that is related to the observable delta TV, and here are some interesting physics parameters that we might be interested in: the density delta, the xh1 that you asked about, and the peculiar velocity. Apart from the TS, of course, which as Kanan and Prasad have shown, has already a lot of astrophysics inside. Okay. So in fact, if I now plug in my background, if the background is CMB, okay, it could be something other than CMB. If background is CMB, then I can just plug in the CMB temperature in my radiative transfer equation. So it's the CMB temperature that will get attenuated, the CMB intensity that will get attenuated, and then I can write my observable as simply okay. The difference, the contrast between this is just the radiative transfer equation written in different terms with this 1 plus z factor coming in because now I'm writing in the observer frame, and then this tau nu naught comes in because I'm just expanding because this value is very small. I'm just expanding the exponential. And again substitute these numbers and write down what this means. This takes the form of, if my correct, it takes this form 1 plus z square root. This famous term T gamma by Ts. Right? This is the important combination that all of us should have. Right? And then this peculiar velocity. So if the spin temperature is very large compared to the CMB temperature, then this thing will go to 1, and then the number will saturate to a value. But if spin temperature can be reduced to much smaller value, then there is no lower bound. 21 centimeter signal can keep increasing. So this is the logic which Hera recently applied to put limits on X-ray heating. There is no limit to how low this can be. There is a limit to how high it can be. Okay, so now that we have introduced these parameters, yeah, so what we have done, so what we have essentially done is we started with the radiative transfer equation, which connected the observable, namely the brightness temperature, to the opacity tau, the optical depth tau. We then wrote the expression for the optical depth by integrating over the absorption coefficient, which we wrote in terms of atomic physics. And then once we have the optical depth, we took the radiative transfer equation and wrote down the observable brightness temperature in terms of what enters. Once we did that, once we expanded that form, we achieved this quantity here, which has some cosmological terms, namely the density, the peculiar velocity, and the redshift. It has some constant, namely the 9 millikelvin here, and then it has this important term, which is 1 minus T gamma by Ts. And the limit that I said was, if Ts is less than T gamma, well, if Ts is less than T gamma, then Tb is negative. So you have an absorption. You have an absorption signal. If this is greater, the spin temperature is greater than T gamma, then you have an emission signal. This is another attractive feature of 21 centimeters, that it can have both absorption and emission. This is actually used in many papers because the sign change redshift is given great significance and do a lot. And the limit that I gave was this TB today. If yes, when will it saturate? When this goes to 0. Right? So this will go to 0 if the spin temperature is much greater than. We will consider in under what conditions the spin temperature becomes much greater than CMB temperature. So I guess many of you already know that. But if you don't, we will come to that. For the moment, what is to be taken away is that there is a regime where this thing becomes a constant. Okay? So the maximum brightness is unfortunately limited by this. The minimum is not limited. So TB is not counted if Ts is now very small. So if Ts is small, you have an absorption signal, as I wrote here. However, the magnitude of that signal is not bounded. You can keep it. So indeed, some of you might be familiar with this nearly charged dark matter cooling papers, where the Ts can keep going as small as the model permits, and then as Ts goes down, the delta Tb also keeps going. Okay, so I think we have made a very interesting connection between TB and various parameters, delta XH1 TB parallel by DR. Okay, and all of these connections are really interesting, very interesting. People specialize in these connections, and the connection that has received the most attention is of course the spin temperature, because it is in some sense the richest. There are a lot of parameters hidden inside this. Okay. So what we are going to try to do in this lecture and the next two lectures is try to flesh out this dependence between TS and D. If I understand the relationship between TB and a cosmological parameter, then a measurement of TB by means of the statistical inference arrow will allow me to measure cosmology. If I understand the relationship between TB and TS, then by means of the statistical inference arrow, I can use the observational measurements of TB to measure galaxy formation or reionization, both of which is good. Okay. So this is the game that we play. Delta is the density. Okay, so what I'm going to now first do is I will make some comments on the cosmological parameters later. They are very interesting, but they are conceptually rather boring, because the dependence of these on the fundamental lambda seeding cosmological parameters is rather straightforward. This TS is very interesting. Right? It's something that we are still trying to understand. Lots of debates. So I think I should spend a bit more time on TS than on these parameters. So I will do that, but I will come to these parameters in the last lecture. Okay. So what we need to remember is, as far as we can tell, there are only three processes that can determine TS. Okay, and that's absorption of PhD photons, and then collisions between, Anand has discussed this in very nicely, collisions between hydrogen atoms, electrons, and protons. Explain in detail how these processes affect the spin temperature Ts. Then these equations carry that to the observable TB. And then finally we have the study of UV photon, what Anand called biannual. But we also clarified that this also works for theta. Okay, so then I won't go into the detailed balance equation, which Anand has covered discussed very nicely. But at the end of, so what's remarkable is actually we have a complete census of processes that affects TS. That's already quite a bit of success, right? It's just these three. There is no unknown weird processes that are hiding. It's just some of these can be very complicated, of course, but it's nice that it's a very small list. So Kannan wrote very nicely the detailed balance equation, and then derived the sort of main equation of this field of research, which shows how these three processes operate such TS. So that equation was this, which again Kannan has written. This is also sometimes written as. Everyone probably remembers, many of you know this well. Here we have our spin temperature as promised. Here we have the background temperature, which we are assuming to be CMD. Here we have the kinetic temperature, which is the temperature of the gas, the hydrogen atom gas. And here we have this new quantity called the color temperature, this strange quantity, which somehow determines the brightness of the UV background, the UV photons around the hydrogen. Okay. So this is the most non-intuitive quantity amongst all. So we will discuss that in a second. And then there is this emergence, which again Kannan highlighted very emphatically, of these two new quantities, x alpha and xc, which are the coefficients, which determine how strongly each of these two processes affects the field temperature. Okay, so again, I'm skipping the detailed balance stuff. Discuss this. So what we will do now is first quickly discuss the collisional part. Then I want to spend a relatively longer amount of time on the laminar part. Be complicated, hard to understand. So we start by discussing the collisional coupling. And essentially, to understand collisional coupling, the task is very simple. We want to understand TK. Understood collisional coupling. So we begin by fleshing out a bit what this Xc is. And again, it's not just one species, there are multiple species colliding with each other. And so for species I, we have HCI, we have a collisional coupling coefficient for each of them, and the total is the sum of over all of them is one zero. Okay, so the expression for the coupling coefficient Xc for the ith species is you have your T star, which is the temperature scale that shows up in the Boltzmann statistics equation for the two lines, the 0.0 something. T gamma is the C&D temperature. K10 is just the Einstein coefficient, and C10 I haven't defined, but Kannan did define it. This is the de-excitation rate because of collisions with this species. You use P10, yeah. So that's what we call P10C is what I'm calling P10. Okay. Now our task is to understand this curve. And it turns out that this C10 has been calculated in the literature using quantum mechanics, quantum field theory. Okay. So what has been done is this quantity x I has been written in I, or rather this C10I has been written as Ni, the number density of particles of species I, times kappa 10I. We have a new quantity coming up now. So the good thing about this quantity is that it's a per atom, per particle quantity. Right? It's of benefit to move from C to kappas. And the rest is just as before. So we still have that A10, and then we still have this T star divided by T gamma. And these kappas are available in the literature. Maybe I will, at the end, when we have the projector screen down, I can show. So these kappa 10I are rate coefficient for excitation. As units of volume per unit. Okay. The total coefficient xc, we did not have xci here, we just had xc. This total coefficient we have to write down, and that happens to be just the sum over it. Okay, so this I can be a pretty long list. It's predominantly other hydrogen atoms, electrons, protons. It could be helium atom, could be deuterium, but I guess that's very small. So these kappas, as soon as I have kappas, I can compute XCI. I can plug that in, and I have XC. That's one term done, right? And these kappas available. Okay. Kappas are some collisional, which will depend on the temperature. Kappas, the density dependence of the kappas has been by definition definitely. Okay. Yeah. So sometimes what happens is that these quantum mechanics calculations, they are pretty complex. So they are done only for some values of the gas temperature. And uh, you can't always keep doing the full calculation for arbitrary temperature. Then you just pick a function. By the theory of fitting of function, numerical analysis. In discussion, we can learn how to choose a fitting function that is appropriate. All the risks that fitting any data by. Typically, the distribution as a function temperature is smooth enough. Difficult. Start seeing the function. I mean, there is a huge amount of thinking on how to choose the right function. You can talk later. Not that you will find a lot of discussion in numerical analysis. But there are ways in which you can quite rationally try to choose a function. But the basic idea is the calculation is hard. In practice, you don't have to do it, but in practice, you end up doing it. Okay. Okay. So we have understood how Xc is connected to certain quantities that describe the gas. We said that it is basically connected to this density plus this these atomic physics quantities that we have. But we have said that they are available. So what's left for us to finish the discussion on the collisional coupling is the gas. And the gas temperature is actually, equation is rather simple. The gas temperature evolves in a very well known way, which looks like this. T kinetic derivative with Z has a term that is proportional to T kinetic. This term is just saying that the temperature just keeps decreasing as you decrease the redshift because of the bubble expansion. Then you have a kinetic term 1 plus Z. So that Z divided carry on number multiplied by T. So this is just saying that what is the contribution to gas temperature because of the fact that sometimes number of particles will change because of ionization. And then finally, you have the most important astrophysical term, which is AB a summation over all heating and cooling terms that you want in your. Okay, so this is the adiabatic cooling term which always exists, the lambda feeding universe. This term is because of structure evolving or the chemistry evolving. This term always exists, but this is in practice always subdominant. So this we just ignore. So I have never computed it. Very small. So this is by far the most dominant term, adiabatic cooling. And then we have this most interesting term. If you have a model where there is a dark matter cooling, like this really charged dark matter, then they will add a negative term, cooling term. If you have, I don't know, primordial black holes which emit Hawking radiation and heat up gas, then you will have a heating term, positive term. We will now see how this equation becomes at cosmic dawn. No, this Q is just a volumetric heating rate. This is like the energy per unit time per unit volume injected in the. So this is just energy, and then you are dividing. You are asking how much energy is coming per. You can derive this equation by deriving the energy per atom, 3 by 2 nkt ddt, derivative of 3 by 2 nkt. Understanding how each term evolves. There is an initial condition for this. All we need to specify this is a simple first order ODE. Once you have initial conditions, you can solve this, and everyone knows what the initial conditions are in a normal universe, lambda CDM universe. That's given by the CMB. We know that gas and radiation was in equilibrium at 1100. We know the temperature there. We could evolve this equation with that as our initial condition. Okay. Now, cosmic dawn, one of the reasons why it's very nice to discuss all of this at cosmic dawn is that at cosmic dawn, in a typical normal vanilla universe with no exotic processes, there is just one term here, which is the Lyman alpha heating. Heating because of those UV photons which cause the X alpha. They also cause heat. This can be ignored. There are no other collisional heating or no other. This becomes really easy. We can actually look at some of the solutions. But that's it. So that finishes the discussion of the collisional coupling. We have understood how the XT works out. We have understood how the TK works. All we have to do now is to evaluate this. And in your tutorial, you would evaluate this for many different models of astrophysics and. Okay, but then now we come to the other remaining bit in our field temperature, which is the Lyman alpha bit. Okay, everyone remember that the Ts was T gamma, Tk, and Tc, the color temperature. We want to discuss the color temperature bit, which came with its own coefficient called X alpha. Now we want X alpha here. Again, so this is where things are a bit complex. Alpha is not an easy line. Actually, the attraction for 21 centimeter was that Lyman alpha is not an easy line. It turns out Lyman alpha plays a strong role in that. There is no escape Lyman alpha in cosmology. Everywhere you have Lyman alpha. 60% of Milky Way photons out as line. Now, as a result, actually understanding X alpha T alpha is still an ongoing field of research. A lot of unsolved problems. But the basic process is really simple, which is just this Wauthausen field difference, which can be described very nicely. This is the basic process. The idea is basically you take a Lyman alpha photon, you go to from n equal to 1 to n equal to 2, but when you come down, with some probability, you come down in the wrong hyperplan. Then that is what messes up with the statistics of the two hyperplans. That's the Wauthausen field. Okay, and so that's the X alpha and T alpha is going to be related to, and essentially what we quantify X alpha T alpha is the number density of photons that Kahneman. So Kahneman described this very nicely that in the dark ages there are no sources of UV photons. As a result, this term just goes away. He described very nicely. So the equation just involves understanding collisional, which is the great promise of dark ages astronomy. Because you have a pure cosmological measure. That is why people want to go to the moon, Pratyush, and so on, go to the space to do that. But for the moment, the experiments, what they are hoping to achieve is only a regime where unfortunately this term becomes. But here, our job is to understand X alpha, T alpha, and X alpha and T alpha have to be related to the J alpha, the density or the specific intensity of UV photons. Of course, what will produce this J alpha? Galaxy power. We are introducing this huge, complicated parameter space of galaxies. Who knows? Who understands? Process with a lot of parameters and a lot of things going on. All of that is behind this J alpha. So on the positive side, the richness is why we are interested in J alpha. The hope is that on some day we will understand all those parameters, and then we will take this whole thing backwards using our statistical inference arrow to start determining. And we will hopefully see in the next example a beautiful connection where we will connect this J alpha to JWST measurement and see very nicely how we can actually start learning galaxy formation using 21st century. However, for the moment, what I can say is that this is very hard to calculate. It is not easy. The connection between J alpha and J alpha itself is very hard to calculate. Indeed, what we seem to be realizing is it might be impossible to calculate. But the connection between J alpha and X alpha is also very. But I will sketch the calculation. So let us try to compute J alpha. Let us see what is involved when we try to. The promise is once I can write J alpha, I should be able to write X alpha using the expressions that actually Kahneman wrote down in the write them down again. Okay. So how do you compute J alpha? Now, there is a large amount of literature and it's very hard to read. So our colleague Shikhar has done the hard job of digesting all that literature. He has a beautiful appendix in his paper where he has described 4 totally distinct approaches of calculating J alpha in the literature. I urge you all to read that. I'm going to actually follow Shikhar's paper here, follow his notation, and describe the basic one way of calculating this quantity. And in this way, it helps actually to split this specific intensity into 2 components. It turns out that this is a useful way to do, and we call these 2 components JC and JI. So we say that this specific intensity, imagine this as a background of UV photons at cosmic dawn produced by the first stars and galaxies. We are saying that we want to connect, we have established the relationship between the stars and galaxies and J alpha, and it can be easily done if we split it into these. What are these 2 terms? Okay, so this term is photons with energies between Lyman alpha and Lyman beta. Okay, this is the photons between, not just Lyman alpha photons, not just Lyman beta photons. These are all photons between Lyman alpha and Lyman beta. Okay, and therefore these will be called continuum photons. Okay, if the first stars are anything like normal stars which work on nucleosynthesis, then we will have a Planck-like spectrum to them, and then we will have a continuum. That's this, right? And the point about these photons is that they have energy greater than the Lyman alpha photon. So what happens is if there is a production of one such photon at a distance away from a hydrogen atom, then that photon will redshift until it gets to me. Then, depending on the distance, etc., its energy, it might become Lyman alpha by the time it reaches. So that is the point. Okay. So this gives Lyman alpha by So it turns out that it is important for us to have a separate discussion for these photons. But it turns out that this is not the only photons that exist in this story. There is another photons, and for them we have this extra term Ji. Okay? And this Ji is photons with energy greater than Lyman gamma. So all photons, I think someone asked a question in Kanan's lecture, what happens to these photons? So those photons, Kanan said those photons do matter. He's going to discuss them in his lecture tomorrow or later today. But that term is this Ji. Okay? And these are not continuum photons, these are injected photons. And the reason behind calling them injected is the following. What happens is that imagine these photons, a photon is emitted somewhere at Lyman gamma or some higher energy. You would expect, why is he calling them injected? This photon is going to redshift to Lyman alpha by the time it gets to me anyway. However, what happens is that before it comes to Lyman alpha, it's going to be absorbed by one of the Lyman series lines. They also have very high cross section. There's a very high probability that they will be absorbed by that line. Once that photon gets absorbed, what happens? There is a very large chance that it is re-emitted, scattered as it is called, at the same energy. So it becomes maybe Lyman gamma or Lyman epsilon and is emitted as Lyman gamma or Lyman. But there is a small probability where it cascades down. It disappears. It's not scattered. The photon disappears from the story. Inside the atom, things move so that it finally becomes a Lyman alpha photon. What has happened here? Why is it different from this? The reason it's different from this is now the atom is hit by a Lyman alpha photon without redshifting it. It's as if a Lyman alpha photon at exactly the Lyman alpha wavelength was thrown at the atom. Whereas here, a continuum of photons gradually kept redshifting, and the atom just absorbed photons with energies near Lyman alpha. So this is like having an injection. Precisely the Lyman alpha wavelength, photons are getting injected into the hydrogen atom system. Okay, so these give Lyman alpha. Okay, it's 4 o'clock, so I should wind up and continue tomorrow. So I will describe just what happens next, and we will. What we are going to do next is we are going to take these JC, JI, evaluate them. Okay? And then once we have evaluated them, on the back side of the whole activity is the connection with J, which then gives us X alpha and T alpha. So we will evaluate this connection. And once we have done that, here lies the source. This is galaxy pulse. Here we have things like JWST and so on, and that will help us understand how we model given a galaxy population. If you don't like the galaxy population theory that I am presenting, you can change it completely, but this is where you make that test practically will proceed physics. Okay? Okay, I will resume tomorrow.